All right, so let's talk about Kullback Leibler discriminant analysis. So KLDA is an interesting method in 2007 IEEE conference. And so Kullback Leibler, as you have seen in my previous lectures, is a measure of separability of any two classes by viewing them as a probabilistic distributions of training data. So what we want to do is just to maximize f of a, which is all different combinations of Kullback-Leibler divergence between any two class I and J. For example, Pi A transpose X. A transpose X is after projection, and also Pj A transpose X. So Pi A transpose X is a sample distribution of classes I and J after linear transformation A. After you have done this linear transformation, this is your sample distribution. And the authors didn't use the traditional KL divergence definition. They use a symmetric version of that. So symmetric version, KL of Pi of X and Pj of X. So Pi and Pj of X is the symmetric version is like this: Pix minus Pj X log of Pix over Pjx dx. You may ask, why is it symmetric? Okay, just write Pj of X and Pi of X. Let's work on this. Pj of X minus Pi of X log of Pj of X, Pi of X, d of X. So if you just change these two probability distributions, your solution does not change. It's like a matrix, in matrix space. The distance, for example, between point A and B is like the distance between B and A. So it's a natural measure of distance. So if we just work on general multivariate, simple Gaussian, if you work on simple Gaussian and apply this Kullback-Leibler formula, you will see that, in simple Gaussian, you have mu, mean mu, and sigma as your covariance. So you can write this as, you have seen my previous lectures how I calculate Kullback-Leibler or divergence between simple Gaussian distributions, between multivariate Gaussian distributions. So it is as simple as this. Inverse of that, and mu I minus mu j plus trace of sigma I minus 1, sigma j, plus sigma j minus 1, sigma I minus 2i. And here, because we should approximate mu hat by sum of xi, we have nj samples, and xi is in class J. Also for the covariance, we should approximate it, so it's empirical approximation of that. So this becomes xi minus mu j, xi minus mu j transpose nj plus lambda id. They use this term and lambda because this is a regularization parameter to make the matrix inverse operation numerically more stable. And so it's a simple trick that we always use. Okay, so let's carry on by the transformation. In transformation, you have seen several times that the mean is transformed like this. And the covariance is transformed like this. And one thing that you should know, that the 80th formula in the cookbook, Matrix Cookbook, is, if you look at that book, you will see that it is written that partial derivative of x transpose bx, xij, is x transpose b, jij, plus j, ji, bx, where these jij, the kth coordinate of that is just delta I, k, delta ji. So knowing this, you can write KL divergence between pi A transpose x and pj A transpose x as A transpose sigma I A minus 1 plus A transpose sigma j A minus 1 A transpose mu ij. So I'm just substituting that to see what happens. A transpose sigma I hat A inverse, A transpose sigma j A plus A transpose sigma j A minus 1, A transpose sigma I A, and finally minus 2id. So trace of this. And so you should know that each KL ij is a non-convex of A. So f of A is non-convex. So finding local maximum using gradient-based algorithm, given initial estimate of A. For initial estimate of A, you can use conventional LDA for initial estimate of A. So you get a suboptimal because it's a non-convex, but you can use methods such as successive convex approximation, majorization, minimization, or minorization, maximization, and difference of a convex function method. There are lots of methods to deal with non-convex objectives, non-convex problems, because they have lots of local minima or local maximum. So finally, you can use you can write KLij as the sum of two parts, KLij plus KLij. So this is just the 2007 IEEE conference article that he has written it as like this because it's a long sum, so he has separated for clarity. So this one becomes mu ij hat mu ij transpose A transpose sigma I hat A minus 1 plus A transpose sigma j hat A minus 1 plus 2 sigma I hat A transpose sigma I hat AI minus 1 A transpose mu ij hat transpose A transpose sigma I hat A. So it's a long sum. Minus 2 sigma j A transpose sigma j A inverse A transpose mu ij hat transpose A transpose sigma j hat A inverse. And so you can now calculate the gradient of f of A with respect to at point, I mean your point is matrix. At matrix A is equal to I is equal to C minus 1, J is equal to I plus 1, C, omega I, omega J, KL, I and J. So we can use a conjugate gradient. You know, we use it because we can use iteratively we can calculate A and find A, because if you find A is your transformation, so your discriminant analysis is done. H of t, and you know, H of t is G of t plus gamma t H of t, and this G of t is gradient of f A t plus 1. So you see that he has used conjugate gradient to come up with this to solve A numerically. I mean, as a scientist, you should always do critical thinking when you read any article. You should understand the pros and cons of each article. For example, this article, it is written in 2007. It's an IEEE conference. I mean, I like that because he has used the KL divergence as a measure of similarity between two sample distributions of class I and class J. That is nice. The thing that I don't like, and is just because he has assumed that it's just a Gaussian distribution. This is the weak point. And because you only have mu and sigma, mean and covariance, and nothing more, and the data could be much more complicated, even if you model it as a mixture Gaussian, it is much more complicated in reality. The reality is more general than that. The other problem is that it doesn't care about locality too much. For example, there are some methods such as, in dimensional reduction, they use Laplacian operator and all of those that I will talk about it in my future lectures. So they try to preserve locality by, if they transform the geometry in the embedded space is not changed, and so they try to preserve locality. But this method does not care about locality. Even if it cares implicitly, it has done by that Gaussian distribution. And the other thing that this method doesn't care is what if you should do a semi-supervised learning? I mean, you have some labeled data. It's not infinite. You have just maybe 20 or 200 labeled data, but you have thousands of unlabeled data. Labeled data is very expensive. We cannot find it anywhere. It's hard to create them, but unlabeled data is, you can find it. I mean, Google has many of them. That's why it's the first problem in Google. So you have to deal with semi-supervised learning as well. The other thing that this article doesn't care about is that in reality, you get your observations in an online fashion. So things like online optimization and those things matters. So the last thing that I want to mention that I don't like is that this article, in one of the sentences, they say that, okay, you can find local maximum, no problem, given an initial estimate, and they use, for example, initial estimate of conventional linear discriminant analysis. Okay, no problem, but why do we care about non-convexity? I mean, even it may not even be a very suboptimal point. So the problem is a non-convex problem, but the authors don't care about the non-convexity and say, okay, a local minima is enough. It's just like those people who do deep learning. They just say, okay, we have a magical tool. They call it stochastic gradient descent, and it does everything for non-convex problems. So we don't need to care about anything. So they don't need to care about non-convex problems. But the future of deep learning, I'm sure one day everybody will talk about successive convex approximation. Everybody will talk about majorization, minimization, or minorization, maximization if they have maximization problem. And methods such as difference of convex functions. And those great methods for dealing with convex problems. But here, this article doesn't care about those things. And of course, I really like this article, despite the weakness of dealing with several issues that I've just mentioned. I like it because they use KL divergence, and the formulation is quite clear. The methodology is quite interesting, and but they have weakness as well, and that's it. So in the next lecture, I will talk about another method, which is locality-sensitive discriminant analysis, which is done by people in Yahoo, Google, I think, and Yahoo, and I don't remember. But it's a great article because it is written in 2007, the same year that this article is written, and also it has great citations. I mean, more than 100 papers is written to just generalize or use it in practice, and so it's a game-changing article because it influences all researchers. Those articles are very rare, and because they are very natural. I mean, the most natural way to deal with a problem. And so I will show you how they use locality-sensitive discriminant analysis in the next lecture. And because linear discriminant analysis fails to discover local geometric structures. And when data is not sufficient, local structure is generally more important than global. And nearby points with some label are close to each other, and nearby points with different labels are far apart. And these important constraints are formulated very interestingly. Instead of just a traditional Fisher or discriminant analysis, we does care only about the mean. Mean is nothing. Mean, what do you mean by mean? Mean is just one thing, but you have second moment, third moment, and higher moments. A distribution is much more complicated than just the first order moment, which is the mean. And so I will talk about how they use the two graphs, one graph for within classes, and the other graph is between classes. And so I will formulate it in the next lecture, and their solution, is just a maximum eigenvalue solution to a generalized eigenvalue problem, just like many problems that I've just mentioned in spectral clustering, in Laplacian eigenmap, in many locality linear embedding, all those dimension reduction methods. And so generalized eigenvalue problem, this generalized eigenvalue problem, you can see it in all parts of machine learning. And that's why it is, historically, it is related to Cauchy, it is related to Rayleigh quotient problem. And but okay, so in the next lecture I will talk about